So hi, this talk is going to be about building distributed systems with the use of LabVIEW and ØMQ. And I want this to be kind of a discussion of how you can build a distributed system without a large team. I'm Maciej. I'm a partner at Kolosko. I'm also a CLA and a CMD. I've been doing LabVIEW for approximately 15 years. Let's just jump into the presentation. Feel free to ask questions if you have them as we go through the slides. I've buffered some time at the end for Q&A, but we can just clear up questions as they come along. So first, a general overview of this presentation. So the first thing I want to do is talk a little about the idea of microservices from a very high level, so that to kind of set the stage of where distributed systems are very successful and how they are built. And we're going to just talk about the how they work in the cloud and just basically the cloud-based systems that are very, very successful right now. What is ØMQ and where is it available to use? We'll talk a little bit about the platforms and the programming languages that you can get it on. I have a small demo of connecting the current gen and NXG with the use of ØMQ. So very basic, we'll just go over that. Then I want to talk about a real world example where ØMQ can be used for the kind of systems that people in our community build. We'll have a little bit of a demo and chat about what are stable and what are unstable networks, and then we'll wrap up with a Q&A. So, first of all, I'm going to start by outlining a few aspects of distributed systems. So, basically, they're divided into components through services. That's the first aspect. The second is you segregate your services, and you do that, you orient yourself versus the business capabilities rather than technology. Another aspect of distributed systems, they have a decentralized governance, and they also have decentralized data management. And what I mean by that is if you have a system and you have different services, it's fine if they don't use the same database. They can have their own databases that are going to be fulfilling their own data management needs. You don't have to have one centralized database. They're designed for failure. We'll talk a little bit about that. And the trend is to build smart endpoints and use dumb pipes rather than the other way around. So, what do I mean by dividing things into components via services? So this is a typical monolithic application. We can think about it as a desktop application. It's doing something and it has three major things that it does. If you want to turn it into a service-oriented architecture, you're going to take the aspects that the application is doing and divide it into separate services. And the idea is that you run them as separate entities, separate executables, separate things that are basically running independently of each other. So now I want to go to discussing the organizing versus capabilities. And this is, maybe it's going to be a little bit related to the talk that, the first two talks of the day that we're talking about, how to maybe organize ourselves from a human perspective as well. So if we're building a monolithic application, a lot of organizations, especially if they develop software only, if you're building a big monolith, for example, and it's 30 plus developers, what used to be the trend years ago, you would put the people that are responsible for one aspect of the application, like the user interface, and you bunch them up together. People that are doing business logic, they end up on the same team, they bunch them up together. People that are building the database, well, the database is God, so you obviously need a few people working on the database together, right? And that that was a way of solving the problem. But if we're going towards a service-oriented architecture, what we kind of want is we want to think about like the aspects of our system that are business-oriented, and then build the teams that are responsible for the servers, and organize also our human org chart or like team composition via that kind of matches the software architecture. Yeah. Because this allows the decentralized governance, right? The team that's responsible for orders isn't really relying on the team that's responsible for shipping, because they can have, first of all, they can use a different version of a UI library, or they can use a different internal database. As long as their service is up and the one that's responsible for shipping can talk to the order service, it doesn't really matter how things are working. And this also creates I think, more beneficial experience where the people who are responsible for the catalog, even from a technical perspective, they're going to be thinking about what do I need to do to make the catalog working and be operating, rather than worry about the technical aspects. They're going to put the business at the forefront, and then the technology will follow, right? How do we build for failure? Like, I don't know, have you guys heard about ØMQ, what it is? It's really not a new concept. It's it's an old concept, but basically this CodeMonkey originated from Netflix, and they came up with the idea that if they have everything built through services, they designed an automated tool called the Chaos Monkey that actually goes and turns off your points of your infrastructure, your applications, your virtual machines, your stuff, and on production, right? So they actually run Chaos Monkey in their production environment, and it randomly knocks some services out, and that allows them to design their services that depend on other services to be reliant and expect the fact that anything you depend on can go away, and you have to have a way of handling it. Yeah, so Chaos Monkey is basically a tool that's actually been open source. You can take a look at it, but that's one way of designing for failure. So we were talking about the last point and the last aspect of distributed systems that I had outlined was basically building smart endpoints and dumb pipes. And a long time ago, I don't know, probably like a decade ago, in the enterprise software, there was this concept of the enterprise service bus. It was a very popular thing. And the problem with the enterprise service bus, it was kind of the opposite. It was the smart pipe that was supposed to be connecting all kinds of endpoints with varying ability to be intelligent. And that's kind of what it ended up being. If you want to move through the column, take a look at it, go ahead. But basically it was a bit too complicated and unwieldy. And that's why the design to build, that's why the idea for dumb pipes and smart endpoints kind of originated. So now that we kind of set the stage and talked a little bit about cloud-based distributed systems, just to have an idea, what's ØMQ? So it's not another message queue or anything. It's not a daemon, it's not a server, it is a library. And it doesn't bring any additional dependencies with it. It's basically a single C++ DLL, and that's it. You include it in your project, it doesn't bring any friends. Even, it used to have a GUID dependency on the library to generate unique identifiers, but that has been refactored in a way that the library handles it itself. So it depends on absolutely nothing. And it's a lightweight, and it's built on the socket system. One of the catchphrases for ØMQ is that it's sockets on steroids, and I think it's a very, very fitting way of describing it. And it was originally designed for financial markets, so it is capable of handling a high volume of messages. Right, where can you get it? So there are language bindings that basically wrap over the C++ implementation that I've mentioned, and they're available for more than 50 languages last time I checked. There's C#, Java, C, LabVIEW, Python, F#, Lua, and many more. The C# and Java stack also have separate projects that implement this ØMQ like directly in those two languages. There might be others, but those are the only ones that I'm like off the top of my head aware of. And the operating systems where you can find this library and run it is Windows, Linux, iOS, Android. I've also found information that VxWorks is also there. So how does the binding for the current gen work? So first of all, I want to mention Martin Jasperzi, who's a guy who originally wrote the binding for ØMQ, and he did it, I think, in 2010, because this stuff is really not super new. It's available on SourceForge, so I came across it when we were designing one of the systems. And the concept behind the library, it's quite simple, so I just wanted to have this slide to kind of discuss about it. So on the bottom, there's the ØMQ library, basically the one that does the pure ØMQ DLL. There is one adapter library that Martin wrote, and it basically helps with interfacing the base library with LabVIEW data types. And there is an object-oriented representation, and we're going to talk about two classes here, the context class and a socket class, and that is, I mean, I'm simplifying things, but that's basically it for like what you need to know to get started. So, like I said, the two prominent classes are the context class, and the context class is thread safe, and it basically is, you usually want one context for your entire application, for your service that you're going to be building. And then the context is then needed to be able to create sockets. So sockets are not thread safe, and they manage a single endpoint-to-endpoint communication. So you can have multiple sockets, and there are also multiple socket types. We're going to talk about two socket types in a little bit more detail in a few slides. So, all right, I'm going to jump into my first basic demo to show you how it's possible to use the ØMQ library to connect the NXG and current gen. And so, I'm just going to hop over to my VM. So, what I have here is two VIs, one in the current gen and one on the next gen side. So let's look at it briefly because it's really simple. Basically, what we're doing here is we're creating a ØMQ context object, and then we are creating one socket, which is a request and reply socket. And then we bind the socket, which means that in this case, there are two things that you can do with sockets. You bind one and connect the other. And philosophically, it doesn't matter all that much which direction do you go into. It's the only thing that you kind of want to do is you usually want to bind with the socket that's more stable in the network, which means it lives longer, right? So the one that's created and disposed more dynamically, that's the one you want to connect to, but apart from that, connecting and binding is very similar. So what this example is going to do is just going to do a request to reply. So basically it's going to receive some data and send some data back, and that's it. On the NXG side, things look very, very similar. We also create a context, we create a socket, we send and receive, and we'll talk a little bit about the differences here in a sec. So I'll just run it.
Does it matter what order you were in?
Nope. And that's the thing that I actually wanted to emphasize. It's just a few VIs here and there, and it doesn't matter what starts first, what starts later, which one you shut down, which one you shut off. Like, everything is handled for you. That's why the title of the presentation is how to build a distributed system without a large team, because like if compose systems, there's like 7 of us. On and off, like 3 or 4 of us will work on a single project. Like we don't have an entire 30-man team to be building this stuff. So,
Right. So let me just run this guy. So, and basically, what is a message? So in here, like the message is a is a string. So I'm running from the NXG, I'm sending a message hello there, and it's just like basically counting out the iterations of those 2 loops and running. If I stop this guy and I run him again, one of the iteration loops like stops, but everything seamlessly reconnects, right? So you can obviously, you have tons of options on your socket. You can set timeouts and behaviors on how they should behave. By default, the timeouts are pretty much infinite, right? That's why, like out of the box, when you run it, like it doesn't matter if I stop this one, and then I run them again, they're just going to reconnect, and just the loop counters, as you can see, reestablish themselves. Now, one of the things that's specific to, so like I said, everything, the message is basically you can think about it as a binary string, but it's actually like a byte array. So one of the things that it's important to note, LabVIEW NXG has changed the way it thinks about strings. It no longer, like strings are UTF encoded rather than ASCII as it was in the previous LabVIEW. So in here, I'm just gonna type in a few characters that are kind of like weird for the old gen. So one of the things you need to keep in mind, that this is LabVIEW specific, your encoding has changed. So I'm thinking about the stuff that I'm sending from next gen as a pure byte array, but like if I change the encoding back to the ASCII encoding, things are gonna fall all into place correctly, right? So, right. So that's like a quick demo. Any questions at this point, or?
In your next gen code, you have an IP address there, but in your current gen, you don't. You have a long premise.
Yes, because it's like, so this is the difference between the bind and connect. Bind basically opens a port. I use 45555 for this demo, and like the asterisk here means it'll accept connections from all over the place. I'll have a demo on this later, but basically that means that I'll talk about the socket patterns, but that kind of means that to this socket, which is a request and reply socket, you can connect multiple other request and reply sockets. So you can basically have a lot of other nodes requesting, and this one's going to be replying.
It doesn't care about who's actually talking to it.
It actually has an internal logic there that it'll take a request from this guy and reply to this guy, and it'll take a request from another guy and reply to the other guy, right? Although in this loop, it'll just block those requests, but it would queue them up, right? So if you have 2 nodes that are requesting, if the first one requests and the second one requests, the request from the second one will wait until the request from the second one is fulfilled, and then automatically will give you back the request for the second one. And that allows you to build networks that kind of make sense with like little effort as a programmer, because things mostly behave as you would have expected, right?
And that's because of the ZMQ REP option that it has that behavior.
Yeah, I mean, like a lot of thought has went into this library, and it's, yeah, it has like, it's very well thought through, and it has multiple engineers and multiple projects built upon it, and that's why, like as a small team, I think it's a good library to jump into. Okay, let me just take a look. How much of the time?
So you have your message data as a string. Can you set that to, like, let's say binary to increase data throughput?
There's like a binary string is basically the same thing as a binary U8 byte array. So it won't. So maybe I made a mistake of calling it a binary string. It's basically an array of U8s. It just happens that in LabVIEW current gen, like we basically make an array of ASCII as string,
So each one of them is 8, each one is a byte. So it converts to an array like basically with no conversion. But the messages in ØMQ is basically a byte stream. So it's quite performant. And so what we see here in LXG, maybe I'll just show you quickly. I am basically using a byte array here. So it's basically an array of U8s that's being sent over the wire.
So this provides a transportation layer, but there's, I don't know if I'm getting the terminology correct, but there's still like a protocol layer above that define what kind of data you're actually sending.
It's totally to the nodes that receive it to decrypt what the message is. There is a little bit of padding added to the message, but it's like very little. It's like there's some addressing that's being, yes, there is some protocol that's being added to the message, but most of the time once you get the message off the terminal, it's on you to figure out what it is, right?
But if you wanted to send that cluster, for instance, you have to flatten JSON or flatten XML first.
Yeah.
And then on the other side, know what you're flattening it to.
Yeah, and also like since this library is quite simplistic, like there's also no security that comes with it. Like if you want to have some security, you have to build it on top of it. This will just like transmit the data for you. All right, so.
Do you know, is it built on TCP/IP or can you do other protocols as well?
There are different transports, but yes, what I've been demonstrating to you is TCP. One of the last slides talk about the different kind of transport that right. So we demonstrated that. So like, let's talk about a real world system example that it's the kind of system that we build in LabVIEW that could benefit from this. So I have a diagram of a system that has nodes distributed over a local area network. And some of them are basically LabVIEW current gen. Some nodes are C++ based and some are C# and .NET. And this diagram kind of depicts a real-world system that we're working on where we've used ØMQ. So we have like an assembly line where we have a whole bunch of robots that we control through a third-party software that's written in C++. So we wrote a plugin in this software that goes over ØMQ and basically allows LabVIEW to poke in a message and get a message back to tell our software to do stuff with robots. There's another vision inspection suite that is .NET based. We use a very similar kind of technique of poking messages in and out. And then we have a LabVIEW control program that is like a bigger sequence in mind, and it talks to a whole bunch of other stations where we have, I think it's pretty much one to every robot, which are totally in LabVIEW, right? And they also talk to each other over ØMQ. So they poke a message here, get a message there, and every single one of these entities kind of lives in with their own life, and there's different people developing different stations. So as long as the service and the contract that's being provided is maintained, it doesn't really matter what's in the background. So for example, these nodes don't even know or care that there is like other stuff that's done LabVIEW. So that's kind of like a real world example where this stuff kind of is implemented. What we found, like playing around with this, that for communicating between LabVIEW to LabVIEW, an easy way that at least worked for me would be to send LabVIEW objects as messages and just flatten them to string and unflatten them on the other end. And as long as things are serializable, this works pretty well. And just like you can, as long as the message that way it's easy to unflatten the messages. I should basically say not LabVIEW object, but LabVIEW cluster. Yeah, when interfacing with C++ or .NET, JSON has been my tool of choice. Although like you can do pretty much whatever, but I basically take a LabVIEW cluster, flatten it to JSON, and then on the other end, unflatten it from JSON to an appropriate object in that programming language of choice, and that's how they talk to each other. It's very, very simple, right? And in LabVIEW and XG, yeah, I think G types are a good thing to flatten the JSON. So communication schemes. The example that I've shown you was based on a request and reply socket. And that socket is basically, it works like you cannot have two requests in a row. You have a request, and then you would need to have a reply, then you can serve another request, and then you get another reply. So it's like a...
They're not buffered.
They can be buffered.
Okay.
They can be buffered. In the example, if you're talking one node to another, they won't be buffered. But I was talking to Mark about the example of like having two requesters and one responder, like something like that. So they will be buffered. So for example, if this guy makes a request but it's still being fulfilled, and at the same time this other guy makes a request but it's not fulfilled yet, his request will be kind of buffered and served as soon as reasonable, right? As soon as whatever loop is handling this is released to make a reply. So I don't know, it's not really buffered, but it's sort of buffered.
It's kind of a buffer based on the requester, not on, so requests from the same requester are not buffered.
Yes,
Yeah.
yes, that's correct. And another socket that I just want to, there's more types of socket. There's also router, dealer, there's a push and a pull, and an exclusive pair, but like just to cap the scope of this presentation, I just figured I'm going to talk about the most common ones. So request to reply and the publish and subscribe. And the good thing about these sockets is that without any additional infrastructure or plumbing, you can add as many requesters as you want to your structure. And with the publish subscribe, I think publish subscribe is a very easy example to understand. You have one publisher, multiple subscribers. You can have as many as you want. And in this case, the messages, they're not really guaranteed to be delivered. If you're there and you're listening, good. If you weren't there and you weren't listening, you didn't get it. But like, it's appropriate for certain design.
Publish subscribe is it's not topic based, it's socket based.
It is socket based, but you do have an ability to envelope messages, so you can kind of like subscribe to a specific
So there are
topic.
built-in filters.
There is a built-in filter, yes. I just talked about it very briefly, but it is possible to do.
Okay.
Now, one of the things that just by knowing these two sockets, I wanted to like give this example and what you could build with it, and you can even build basically a multiplayer game, right? Using just a publish and subscribe and a request to reply. You can imagine that the client, there's a server that basically holds the game state. You have a request and reply where you basically tell your character to move somewhere or do something. And then you have a publish socket that can publish the changes of the state or the current state of the world, right? So basically through the publish and subscribe, you can know what's going on the server with the game. And with the request to reply, you can basically make requests and reply to like move the game state by your player. And then you can have other clients come in and go in, and just by knowing these two sockets, you can build stuff, right? And like I said, there's like 6 other socket types where you can actually, the one that would buffer work would be the for example, push and pull, I think would be a better one to think about. Right. And also, with those 2 socket stack that I just described, you can also build synchronous and asynchronous operations, right? If you want to have a synchronous operation, you can have a client that makes a request and gets a reply and gets a synchronous operation. And if you want to have a synchronous operation with kind of like an acknowledged promise that, yeah, I received your message, I'm going to do it for you, and you can then listen to another socket that's a publisher subscriber. If you care, you can synchronize yourself with it. If you don't care, you can just like, you can just go off the promise, right? And there is a possibility to add message envelopes. So basically what Dimitri was just asking. So if you want to only listen to specific replies or specifically predefined messages, you can configure that. So now I want to talk about stable networks. And yeah. I'm just gonna let this play out because it's just good. Right, so I talked a little bit about the bind and connect, and what is stable and unstable design. And basically, you want to use bind for those endpoints that are stable in your network, that you know that are going to be there or that are supposed to be there. Whereas connect is for the ones that are going to be coming and going dynamically. And how does it influence our design? So I have a demo that kind of demonstrates this pattern, where there's going to be a few requester sockets, and there's going to be 2 sockets in between, a router and a dealer, but they are going to be stable sockets. They're going to be at a fixed location. So basically the entire network kind of depends on this guy to be able to, like, these guys can come and go, these guys can come and go. This is like a stable point of the network. So let's just demo that. Back to the VM. So what I built is, in current gen, I have the responding socket. So I'm going to start one instance of a VI, basically cycling through a bunch of images, and another one that's going to be cycling through another bunch of images. And what I'm going to do is I'm just going to put a proxy in between. So this proxy is basically, it has a router socket and a dealer socket. So it's going to be like that stable point of network that I run. So I said I'm just a proxy. And then in NXG, I'm going to run a few request and response. So I just ran one of these. I think the one with the US images, I don't think it's from it. Right. So now on the NXG side, it's just getting round robin, right? So it gets one image or the other, right? And those images are basically flattened to a byte array and transmitted, and like that's how it works. Right? I can go and spool off like more of these clients if I want to. So they'll just join the network and just like keep getting the images. I don't know why it's not mixing them. Did I screw something up?
Is it supposed to be going all the images?
They should be being mixed. Oh yeah, they are being mixed. No, for whatever reason, I see them being the same.
You just get these a bunch more and then a bunch of the other.
I think this VM is just like reached the end of its. I think it's pretty overloaded. Yeah, but I stopped the US ones. So I think it was working. I was just like being unlucky with how things are getting buffered. But I stopped the ones with the US images, and the network is still going on. It's still working. And these guys don't really know like what servers they were going through, right? The router and the dealer was kind of sorting it out for them. Let me just re-enable this.
You need to change the publish rate. And
Yeah, I think the publisher.
you'll have a different situation.
Yeah, because now they are being mixed. They're just like, yeah. But what I want to show is that if I go and, because this is a stable network, if I just shoot the proxy, everything stops. And it's just gonna, like, this is not serving because it's not getting any requests, this is not getting anything because it's not getting any responses. But as soon as the proxy is back online, the system goes back into live, yeah, so everything reconnects and like gets itself back up, right?
Is there any loss of data?
So if we're talking about a publisher and subscriber pattern, like there would be a lot, if there's nobody listening, it doesn't matter, right?
Okay.
There was no loss here because this is all based on a request and reply. So when the proxy died, like the servers only served when the clients request, so there were no requests coming, so the servers weren't serving. So no, in this design pattern, there was no loss. There was just like everything halted until it came back up again. And it really depends on what you want to build. But with the sockets that you have available at ØMQ, you can build for all, pretty much, I think you can build for any case that you could think about, right? And it's, okay, that's what I had for this demo. How are we doing for time? Okay, I do have one more pre-recorded demo.
So would you say there were, I guess, compare back to LabVIEW, that request for reply would be more like a queue and publish subscribe would be more like a notifier?
I would say not a queue because like from the same client, you can't request again until you've gotten a reply. So you can't like queue up your requests. You have to build up that queue kind of on your own if you wanted to buffer the requests. Because the request reply isn't a queue. You cannot request again until you've gotten a reply. If you request twice from the same client, you'll get an error from ØMQ saying you haven't gotten a reply yet. You need to wait. Yeah? But there are other sockets that will allow you to buffer stuff. I don't remember off the top of my head, but you use a different socket type and you can have a queue. All right. I do have one more demo, and this one is actually like I recorded a video, so I'm just going to run the video and narrate it. This is basically an example of an unstable network where everything can come and go as it pleases. So the reason I pre-recorded it because it involved basically two virtual machines. So I have one virtual machine with the like IP ending at 17, and So what I'm going to be doing is I'm going to be spinning off two separate executables. The first one I'm just going to call it 1, and I don't know if this is all visible well enough for you guys. I don't know how I think you can see it. Yeah. So 2 systems are up, and what they're using is they're broadcasting on the network their existence. So basically, there's like one main socket, and the port is being generated automatically, where they kind of broadcast their existence. And then I'm going to go to one of the services and basically create some sub-sockets where you can have, so one socket serves one service. That's kind of the idea behind this small application. So I'm going to offer some services on one and list them on the other. Yeah, so I'm going to offer and list. So now this one sees, oh, okay, on my network, if I create a network, this is what I can do on this network. And the other way around, if I offer a service from the second node, I can list them onto this one. And everything's unstable, so when things go on, there is no fixed point. They kind of discover each other. So everything demonstrated here is basically on a local. It does go over TCP/IP, but it is all kind of local on the same machine. And I'm just going to speed things up. Here I'm jumping to a second VM, which has the IP address ending in 9. So I'm just going to spool off another endpoint. Call it number 3. Launch it. So it sees the other ones. Takes a little bit of time for it to UDP broadcast its existence. The other ones can see it as well. Then we can list the services offered, and Now, it sees the other two nodes running on the other VM, and it can figure out that two services are visible from one of the nodes, the other service is visible from the second node.
You said UDP?
So UDP to discover, and then TCP to do the services. So this
Is there a
discover-
UDP support for ØMQ?
No, so that's kind of the thing that was rolled externally to this. So in order to kind of discover the services, they broadcast over UDP, and then that UDP broadcasts a single socket that allows you to discover all the other sockets, right? Because I wanted to show a completely unstable network. So here I shut down one of the services, and the services went offline. If I run it back and republish the services, it will come back online. And this goes back to the idea of building your services in a way that they can handle the outage of stuff that they depend on, right? So I basically did what Chaos Monkey normally does in Netflix infrastructure. It goes find some service and whacks it. And the idea is that the other ones that are still online, they're not supposed to crash. They're supposed to make some reasonable assumptions or wait a while until they continue. Okay, so. Oh, that's not what I want to do. So last thing, there was a question at the back, like what are the modes of transport that are available in ØMQ? So there's TCP, that's the one that's good for crossing the boundaries of PCs. There's also in process, so basically that's ØMQ, but when you do not cross the boundaries of an application, but you want to use ØMQ to communicate between threads, your ØMQ code is going to work pretty much the same if you just switch the binding from TCP to in-prots. The only difference is that in in-prots, the end that binds needs to be alive first before you connect to it in the thread-based communication. It doesn't handle the connect first and the bind node starting up later. But apart from that, it works the same. There's also IPC, which is inter-process communication, and that one's only supported on Unix and Linux systems. For Windows, what you do is you go over TCP and just bind to localhost, and performance-wise, it's pretty much the same. There was just no facility to do this, the IPC that way on Windows, right? But like through reading the documentation, if you use local TCP, it's pretty much the same performance as in between processes. And there's also another way of using ØMQ for, so everything we talked about right now is basically unicast, so it's like one node to another node. There is a multicast capability, which is built on PGM, it stands for Pragmatic General Multicast. If you have application requirements where you want to, I don't know, stream video from one node to multiple nodes, and you need to make it sort of reliable, but like the Pragmatic General Multicast, it's not going to be perfect. You basically index packets, and if they get lost, you can retransmit them with PGM. But there's only so much like buffer that you can have. Yeah, if you're streaming video, you can probably, I don't know, maybe buffer half a minute, 2 minutes, but sometimes you're just going to lose some data if your node is not connecting. But PGM is a good multicast solution if one's necessary. And Yeah, I did have one slide to just talk about zero MQ termination. I found it wasn't very clear in my beginnings on how to clean everything out, how the sockets get reaped, and how to get rid of them. So I just put in a link to the zero MQ termination for people who are getting into this. Bear that in mind when you're shutting down your application to take a look at this. To know that, for example, if you create your context and you tell it to destroy all your sockets and you didn't expect to do it, well, surprised as I was. So it's just like a, yeah, I've left some time for questions. So
How much has the zero MQ binding changed since 2010, and how much did you add to it at all for composed systems?
to the binding, so I basically, when I worked on the proxy, that the router dealer example, because we were intending to use it in a system, I found some issues with it. So I did make a small bug fix to that. Apart from that, everything that I found was enough for me to build the system.
That was
Right.
bug fixed to zero MQ itself?
No, that was a bug fix to the LabVIEW layer of, yeah.
Did you make that fixed in the source code, or?
I've emailed Martin with how to replicate it, because I also I've committed a branch, but I let him handle it. Yeah, so I know that he was reviewing it. I don't know if it's got propagated at this point. Apart from that, I didn't find any things that would be missing from the 2010 version that wouldn't allow me to build my system. I think that the base library is still being actively developed. I did take a look at their Git repository, and there are some comments coming in. But to be honest, it's been stable for many years. So I don't think there's much development to the base library that's necessary.
Do you have to know if the pub sub has an option for lossy, lossless clients, subscribers?
Lossless? I mean, if there's no listener.
No, I mean, assuming that you have a listener connected, and you have any number of listeners connected, if they're all running at different rates or whatever.
Yes, there are.
Sometimes it can be handy to say, I need this pub system to be lossless and try to buffer for every connection independently.
I believe that if you go into the socket options for a socket, there's a whole array of stuff, and I do think you can set up some timeouts to make sure that you're not going to be flooding things over, and I'm pretty sure you can configure it to be lossy.
I mean, you won't like the latest thing, right?
Well, in some cases you want the latest value, in some cases you want to have best effort to not miss any values.
I don't know how to configure it off the top of my head, but I'm 99% sure that's possible through just the socket options to configure it to your liking.
Question for the audience, is anybody else looking to any other type of pub sub solutions, LabVIEW applications?
Message brokers.
Yeah, like MQTT.
What was
You
that?
have a message broker.
FUTC.
No, MQTT. It's like it has a broker meant for IoT applications.
Yeah, message brokers are easy.
Yeah.
In my case, they're three classes, two small ones interface, and one bigger one that does the work. And then you do pub sub, you should subscribe, that's it. So it's easy to write when you know how it works.
Yes. Scalar and all that stuff.
Scaling with views, user-defined events, you can define different message transport. So, for example, a message pending loop that deals if you can subscribe to events that are published by a user, by a message pending loop with user events, so pure decoupled, instead of waiting for large applications.
I have a question. Is it even possible for one of the endpoints to not be using zero MQ? Or would you have to basically build all of the logic yourself?
I mean, that's up to you, your system design. What do you mean? If you want if you want to use a different communication scheme for a subsystem, that's totally up to you.
Well, I mean, sometimes I work in an environment where there's some stubborn engineers that want to interface to my stuff, but sometimes they don't like to conform to what I throw out there. So if I can just say, here, just send these packets across TCP or whatever, and then I'll handle it, I'll just listen for these packets.
Can you write a proxy?
Can I? I never have.
Well, you need to write a proxy that takes their packages and injects them into ÜMQ Types.
Yeah.
I guess maybe you can hand roll a TCP packet to lock it, but I kind of think like, why would you? You're probably better off by including this one DLL
Yeah, and
that nobody even knows that it's there.
you showed that it works with a lot of different languages, and, and I think they use most of those languages. But
Yeah, I mean, like, for example, you can go to, like, if you use C# or whatever, you go to Nugget and you just download ÜMQ automatically, it just gets downloaded. But there's one thing that I wanted to show on the NXG side for the C interface, which I really, I think it's worth mentioning because it's changed, and I think it's changed in a positive way. So I have these, the call from NXG to my ÜMQ send method, which is like a C prototype. And in here, I was able to configure, like, this data thing is a G type. It's basically a G type that I created. And in my library, I have my data G type, and all it is at the moment is basically a wrapper for my unsigned byte array, which is like you take something, you flatten it to a byte array, and then you send it over ÜMQ. So I created this as a data type. But the good thing is that within the C interface, I can actually tell it, look, bind me to this G type of LabVIEW. Whereas in the old, in the current gen, the way that this used to be done was, to me, a little bit less elegant. Because if I go here and,
Still running memory, yeah.
oh, it must be running those guys. Still running? Oh my gosh.
Edit mode.
Press Control down. Yep. Configure. So what's happening here, I'm not defining a data type. I'm actually using a void pointer. So it's kind of less safe because I'm not, like, the interface that I have to see. A void pointer is basically, I could stick in something that I should not be sticking in here, right? So that's why I said that we're using a binary ASCII string, and we're passing the pointer to that string, and then C takes it on. But in NXG, I can actually protect myself, and in the interface define that only this particular LabVIEW class or this particular LabVIEW data type is going to be allowed, right? So.
Did you write the NXG wrappers yourself?
Yeah, but so what I did is I wrote only enough for this demo to happen. There is a feature, I want to port the entire thing, but there's a feature in 4.0 NXG that I'm kind of waiting on to come out. When it comes out, I'll be able to port everything, yeah. And that feature is related with polymorphism. There's, like, NXG also does polymorphism a little bit differently than current. Okay, I think we're at the end of our time.